Hello, and welcome to lecture 21. This is the last of the lectures I'll be giving. From here on out, we have guest lectures as well as student presentations. What is the topic for today? All quarter, I've been trying to extol the virtues of taking a more programmatic perspective on building hardware, right? Using the Chisel language, you can build generators. Rather than building a single instance, we're building a program that can build arbitrary instances kind of, according to some rules. And so the kind of key idea is if we take the best of software to make hardware design more productive, more correct, etc. And so Chisel is a really helpful tool. And what this talk today is going to be about is kind of going beyond Chisel, right? What does it mean to look forward to, what's possible building your own hardware design tools, and what's it look like to kind of not just have this giant leap to go from working in language to, oh my gosh, writing a whole tool, or just kind of more gradual things in between that we can do. I'm going to try and motivate why we're doing this. I'm talking about Fertile, which as I mentioned before, that's the IR that is currently used by Chisel. Um, there are multiple IRs. At the very last slide, I'll list some of the other ones that are currently being used throughout hardware design. But I think Fertile has a lot of great properties. That's why we're talking about it. And to kind of see how it all fits together. As always, we can fire up a notebook. Um, as a small aside, you may have noticed that I have this line here, which maybe looks less like boilerplate now. We've seen this all year. I've been turning off this deprecation warnings. It's for Fertile. So it's not the Fertile is being removed. The Scala Fertile is being removed. It's now being done by a different set of code. It's not written in Scala. But that's been there all quarter because there is Scala Fertile in this lecture. So we've been kind of building up to this. So what are we doing with hardware generators, right? So we're using programming to instantiate hardware, right? In particular, making programs in Scala to orchestrate hardware instantiation. Our Chisel program to keep saying it over and over again, instantiate hardware, connecting it together. Hardware generators are great. We can automate connections and instructions. And what's cool about it is, we can make the design be generated rather than having to keep having to rewrite things, right? And so as you're making these generators, you have to kind of get better and better. You're going through as you're doing your projects right now, imagining scenarios your users are going to be in, all the possible situations they want to use, and somehow provide parameters, let them reach those possibilities, and actually have your generators actually support them, right? And so for some generators, it's really easy to do, or it's a reasonable task to do. But you may see scenarios where it's like, shoot, the kind of flexibility and parameterization I want to enable is kind of beyond what I'm seeing with what I know so far, right? And so the result, it kind of handles more esoteric, more exotic scenarios. You may need to write a lot of code, right? And you go through all this work and complexity, figuring all that kind of stuff out, and you have this maybe just really sophisticated, really clever generator. Um, and that kind of all the insight and all effort is kind of locked into that generator. Wouldn't it be cool to kind of have some sort of resource to enable people to make these more sophisticated generators when they need to, and to kind of share that expertise and that infrastructure across these? And so to kind of make this more concrete for a moment, imagine you're making a generator, right? And it's not just generating hardware. You spend the time, you run your design through some CAD tools. You see, oh wait, this is not as efficient as I would like it to be, and this is a really key component. I got to spend the time to optimize this. Okay, so you go in, you make an optimization, and so your generator doesn't just emit this design, it emits the design with an optimization. And you realize, you know what? Other generators might also want to do the same optimization. So now all of a sudden you have a very different kind of thing. So far in this course, we've been pitching generators, which, as you can imagine, generates a component that provides some specific functionality. Now what I want isn't quite a generator. I want some sort of code I can apply to other code to optimize it, right? So I have this insight of what optimization looks like, and I want to reuse that in other generators, right? So maybe if you're really, really, really clever, if you're Scala and a good programmer, you could try to do this all in Scala, right? You can say, you know what? I'll make this really clever Scala class that, has some sort of generic types, maybe inheritance, such that if someone else wants to build a generator that uses my optimization, they just need to, extend my class and do certain things, perhaps, implementations of certain abstract methods, and, they could do that, right? And so at first it seems like this might work, and the answer is, yeah, it might work. Everybody wants to use this optimization to kind of go through this challenges to do all this, right? That's true. And you got to spend a lot of time iterating, make sure your abstraction kind of makes sense and the things you require people to do make sense. You can handle all of the scenarios. But then all of a sudden you run into some real challenges, right? For example, compatibility, composability, right? Like what happens if you have your specific optimization and someone else wants to have two optimizations in their generator, right? We can't do multiple inheritance. You can inherit multiple traits, right? But you can start to see how it starts to kind of break down. You kind of need to have your optimization somehow be aware of other optimizations. That's going to be hard. What other things could possibly be inside these generators? And you think about like what is the you know vulnerability factor? What is the attack surface you have to kind of worry about? Arbitrary Scala is a very big attack surface, right? It's a very big place to be responsible for, right? How could you possibly handle arbitrary Scala classes, right? It's kind of hard to really kind of get that. It's very broad and undefined. That's hard. So what's the solution? Um, the answer is think about how your optimization fits in. So the approach I just pitched, you have I guess like a templated Scala. You're applying the optimization while you're constructing design, right? An alternative approach would be, what if I construct a design first and then optimize design after it exists? So now all of a sudden, the input output of my optimization before it was, somehow interfacing with Scala of a generator, and generators can be arbitrarily complicated. Now all of a sudden, the input output behavior is I take in a hardware design and I spit out a hardware design. So it's a much simpler, much more restricted domain. And you can also now see how it can be much more compatible and composable, right? Where if someone wants to use multiple optimizations, they can just call multiple optimizations in a row, right? Optimization one takes hardware design in, uh, optimizes it. Then optimization two takes the optimized design and makes the second optimization to it. No problem, right? Because these tools now are all operating on designs rather than arbitrary generators, right? So in other words, sometimes what you want to make isn't a generator, but actually a tool, right? In other words, something that takes a hardware design in and then modifies that design somehow. And so cool. You can imagine these tools would be great, right? They could be more usable, much more general, much more clear to do what you want to do. But then the kind of question is, what does it take to make a tool, right? And you kind of think about where you put in this automation and programming smarts for your design. Do you put in a generator? Do you put in a tool? And as you kind of get familiar with both, you realize it's much more of a continuum than a huge leap. Cool. Questions so far? Okay, everybody's on board with motivation. So to think about that, here's a complexity difficulty trade-off curve. So this one is used throughout computing. I'm using it here for hardware. So think about this as how complicated a hardware transformation is I want to do on the horizontal axis versus how hard it is to build on the vertical axis. So as you've already experienced in this course, right, sometimes writing a generator for a really simple object is a little bit harder than just writing the object directly, right? Here we're writing a generator for a static component. You know what? If it's a really simple design, just write the component directly, right? Now, maybe arguably with Chisel, it's not as hard as it could be, but you could be really simple, right? Now, as that design gets more complicated, at some point, a single static design is going to get really complicated compared to a generator, right? So a generator has a time period where for certain complexity, the generator is going to be less effort. Now, one thing you may notice is that at some point, the generator methodology you've learned so far in this course, the certain language features you've learned, you're going to run into a challenge where, you know what, all of a sudden it gets hard in a hurry. Like the situation I described a few minutes ago, right? Of let's say you don't just want to make a design, you want to package up an optimization procedure and make that reusable across multiple generators. That's all of a sudden going to be way harder to do. And so you kind of have this huge increase in difficulty, making life hard. And so the goal is rather than having that huge, increase in difficulty, can we have a more gradual increase? So it's going to take more effort, but a much more gradual slope. And that's going to be possible what we call a custom transformation. In other words, rather than generating design correctly from the beginning, we're going to somehow modify design, transform design once it exists. Okay, so how can we go about doing that? Well, the answer is you're going to want an intermediate representation. That's a way to kind of carefully describe what the input and output is going to be of this tool. And so an IR, which is short for intermediate representation, is a commonly used tool in compilers and programming languages, right? You have a well-defined syntax and semantics for each component. And so these tools can operate in this, right? It's how you know your compiler stack takes a high-level language and translates it in various ways, optimizes it to finally get correct machine code at the other end. Along the way, it has an intermediate representation. This has been really, really powerful, right? You may have heard of LLVM, which is a IR format for software, but also enables people to interchange what is the front end and the back end, right? And that's what makes IR so powerful, right? For example, if you want to add a new language, then you add simply a new front end, which takes in whatever language you want and produces the IR. If you want to have a new target, you say something that takes in the IR and produces the output, which is sometimes referred to as a backend. Or if you want to do an optimization, you what's called a pass, and somebody takes in the IR, modifies the IR, and then you pass it on to the next part of the tool flow. And so for a long time, IRs are kind of very internal, proprietary details of compilers, whatever. And then LLVM really worked hard to make this standardized and public, and that was a huge watershed moment for that community. So now for hardware design, hardware IRs have also been historically kind of closed source, very proprietary, very arbitrary. They too have become more open and shared, right? So as mentioned in the prior lecture, Chisel 1 and Chisel 2 had something of an IR. It wasn't very formalized and it wasn't exposed. And Chisel 3 was this huge leap by having an IR. And that really made things a lot more possible, right? You can definitely have new front ends, new back ends. It also makes it much easier to implement the thing originally, right? The Chisel 2 was just so freaking complicated to work in that code base. And then now it's working on IR and doing passes, it's way, way easier. So it's, using an interpretation in IR is such a well-established best practice for these kinds of transformations and these kinds of tools. And so hardware is overdue to do it, and it's been doing it for the last few years. Cool. So to kind of show us all fits together, here's a hypothetical world which doesn't quite exist, but I'm showing you what it could look like. So imagine you had a really awesome hardware IR in the middle. That is the kind of key point, right? And so you could have different front ends for different languages. For example, Verilog, Chisel, Pertle. LNAS is a IR from Professor Renau's group here at Santa Cruz. Um, it all gets into this IR. In the IR, you can write transformations that can take the IR in and put it back out, no problem. And then, of course, you have backends, which can spit out. Maybe it spits out, Verilog. You maybe tailor the Verilog to either FPGAs or ASICs. Spits with Plus code for maybe a simulator. Spit out different IR. That's kind of what you want. You want to have this flexibility, right? As you can see, as someone using this large open source code base, you can come in and do things you want to do, right? You want to make a new language? Sure. All you need to do is make a front end to get from your language to the IR, and you can reuse all of this code, right? You want a new transformation? Great. You just need to take the IR in, spit the IR back out, you have a transformation. You don't need to write a whole tool. You don't need to write a parser. You don't need to write an emitter. You just need to write a transformation on the IR, right? You want to support a new output paradigm? Sure, write a new backend. So this software architecture you can see is very clearly very useful. And this is why it's been done for compilers, and hardware tools are now starting to embrace this. So I mentioned this before. Let's bring this home. What is Fertile? So Fertile is the IR that was introduced in Chisel 3, but it's been used in other projects as well. And so, like I said, Chisel 2 and before was this huge monolithic complex code base. In order to do a surprisingly small change, you had to touch a lot of code. It was really hard. It was hard to get contributors because just the complexity barrier was so big, right? There's a lot of bugs. And so, yeah, there's a massive rewrite done where they had Chisel have a front end, it emitted Fertile. And then Fertile itself had transformation passes to operate in Fertile, optimize the Fertile. And then that can, in turn, be turned into Verilog. And so when you hear me use Fertile, both me and the community will often use Fertile to refer to multiple things. It's kind of worth being aware that this is multiple things, right? So Fertile is the IR, which is a specification format. So there is a documentation you read online about what semantics are, that sort of things. Fertile also can refer to a specific .fir file, an actual Fertile file for hardware design. So if you have a show hardware design and you run it through the Chisel front end, you get the Fertile out, you refer to it as the Fertile. Fertile also is a library, right? Which processes the Fertile. And this is the one that has deprecation warnings. So the Scala Fertile library is the one that's been end of life, but is still used in today's lecture. And the reason why is Fertile is now a dialect in a larger IR called Circo, which I'll come to at the very end. Okay, so like I said, in the Chisel tool flow, you have your hardware design in Chisel. It's a Scala program. When your Scala program is running, the Chisel front end emits Fertile, which you think of as a circuit in the actual hardware, and then gets passed on to a backend. So for many years, that was this Fertile Scala library I was telling you about. That generates the Verilog. Now it's a different program, a different code base called FurTools for instance using Circuit, this additional set of code. But you can see that a lot of the things are the same, right? That from the point of view of the chisel front end, you're still emitting fertile, and you can see this is kind of cool, where they're able to kind of introduce this new backend, which has certain properties they liked. It's more scalable, it's faster, less memory consumption. People argue the Verilog produces is more human readable. Um, and that change not only didn't require changes to user designs, it also didn't require necessarily a change to the chisel front end, right? Chisel front end still spits out fertile, and that's fine. They just changed the backend. Um, so today we're talking about this fertile library, the OG backend, I should say. But yeah, so um, if you think about, well, let's dig into fertile because it says it's still the IR being used. What sort of things are in there? How do you express hardware? Um, well, you kind of have this collection of statements, right? There's a variety of things in there, right? So, of course, here I've kind of drawn like an ontology showing how different types of things interact. So your hardware design, of course, at the highest levels of circuit, that's the entire thing. Within your circuit, you can have multiple modules. Okay, that makes sense. Now, of course, your modules, as you've seen, they have ports, right? Input and output ports, I/O. We've seen that. Within your module, you also have statements. So that's things like a connection operation or something. Um, and statements, of course, uh, internally can have expressions. So, for example, I'll say connect A to B. That's a statement. The reference to A is an expression. And so you can see how, of course, statements can include other statements. For example, one statement can include things inside of it. Expressions can include expressions inside themselves. For example, I maybe have, IO dot something. So it's, accessing within a reference. These things all have types. You can kind of see how it fits together. So um, here's kind of talking about the same things again. And you've seen these things and kind of didn't quite realize what's going on. But yeah, I mean, like I said, there's statements, which, basically, think this is roughly one line of actual chisel, would it be a connection, declaration, instantiation, etc. Expressions usually references or literals, or perhaps an operation. Um, so let's go back to our good old-fashioned delay module, which we've seen all freaking quarter, right? In this case, we're not worrying about parameterizing, it's just one register. So yeah, hey, here's the Verilog we've seen all quarter, right? We declare a reg. Remember, in Verilog, reg doesn't mean register, it just means simulation semantics. The actual register comes from the fact that it's going to always block and has the non-blocking assignment. Um, sure, that's the register, that's the Verilog. So what if we looked at the fertile? And so yeah, the notebooks we have for this course, we have this extra, get fertile feature, which has always kind of been lurking there. So yeah, here you can see, here's our design as fertile. So yes, there's a circuit. Inside a circuit, there's a module. These are the IOs. So yeah, it's clock and reset as ports. Has, output. Notice how the out is output, but also it has a flip, which makes this in kind of like an input in a way. There's there. We can see in fertile, reg actually means register. Once again, very clear what happens then. This weird simulation, only semantics. It has all these details, right? What's the name? What's the type? What clock am I using? What reset, etc. And here are the connections, right? I connect the input register to IO coming in, as well as the output, like there. So you see, there's how it all fits together. Yes. Good question. The question is how much optimization has already been done by the time we're looking at this fertile? Um, I don't think a ton. Uh, since we have time, why don't we go digging? So if you go digging around the course code for this course, this is the magic file which enables all of the things that we do in our notebooks. So yeah, it does things like pull in the right versions of the chisel dependencies. Um, when we print Verilog, the Verilog actually normally has a lot of annotations describing where it came from, and I've silenced that with a pretty blunt force of just doing string manipulation. Um, when we call get Verilog, we actually are calling a variety of things within Chisel and Scala to emit Verilog, for example. And so here it is emitting fertile. So because it's in the Chisel stage, which is comparatively in the front end, I would argue the amount of processing is pretty minimal. For curiosity, you might wonder what else is in here. Well, we have something we're going to see later today about how to stringify the AST, sure. Generate visualizations using the GraphViz tool. That was something we saw in the second lecture. Um, Here's something I wrote a year ago for doing a waveform in the notebooks. It's still in here. The reason why I use it commonly, it's not super helpful because the aspect ratios aren't great, but maybe someone watching this gets excited about this and wants to go fix the style sheet. Much appreciated. Um, okay, let's move on. So, uh, as I just said, right, we can print out the AST, right, see all the fertile files. So here it is, kind of written out. Um, and so, yeah, this printing is actually not the worst. It actually does kind of group things together better. If you're a person like me who's done research on Fertile, using Fertile, that sometimes you get this. This is, impenetrable for humans. So this kind of formatting is a way nicer two-string formatting. If you didn't have that nicer two-string formatting, you could use the stringify feature to kind of also get a similar clarity. So cool. So here we are looking at, Fertile for a given module. If you actually were to try to draw this out, this is an example I drew in this course style using from the original Fertile paper. Here's all it fits together, right? You have your module. Above that, not shown, of course, is the circuit. You have your ports, right? Okay, yeah, clock, in, out. Sure. You have statements. This is the block of all statements. There's a register, and there's the connections, right? We're saying, oh yeah, by the way, this register as a type and a clock, right? I connect the register to the input, I connect the output to the register, etc. So you see how what was a really simple looking module actually has all these things kind of at a language level. That's kind of how they all fit together. And so, kind of point of today's lecture, like I said, is to kind of show you what this looks like under the hood, but also to kind of motivate what you can do by viewing hardware in this way. Cool. So how does Fertile actually work? So that Fertile library, which takes in this Fertile we just saw and turn it into Verilog, right? Um, the way it does that is what's called passes, right? So um, rather than going all the way from Fertile to Verilog in just one big function, that'd be really hard, right? We want to make this into bite-sized pieces. And so this is a technique using compilers, this kind of nano pass, micro pass procedure, where basically do one small thing at a time, and you do many things in a row, right? And so by having each of these passes do a single thing, it's much easier to specify what a pass is supposed to do, reason about what it's supposed to do, and most importantly, much easier to test that pass to make sure it's doing the way you expect it to, right? This is something that's done in compilers. It's a great best practice, and it's being reused in hardware, right? And so Fertile, as it goes through these passes, actually has specifications for what these abstractions should be at multiple levels, right? So there's a notion of what's called high Fertile. That's the Fertile basically comes nearly out of the chisel front end. And then there's low Fertile, which is Fertile that is very close to Verilog. So basically what this compiler is doing is it uses the term lowering, where you start from high Fertile, comes out of that chisel front end, and gets progressively lowered down to low Fertile. So in other words, you take these high-level abstractions and you simplify them. So for example, high Fertile is something like a when statement, which doesn't really quite exist in Verilog. At some point, that when statement needs to get turned into a mux. Additionally, in high Fertile, as you've seen when you're in chisel all quarter, you can sometimes not specify things like bit widths, and the bit widths can be inferred. Bit width inference is one of these passes, right? And so that's one of the steps that goes from there. So technically, in terms of how things are specified, high Fertile is actually just all of Fertile, and low Fertile is a subset of Fertile that's, as the name implies, very low-level features that are very close to what's Verilog requires. And you're basically going from low Fertile to Verilog is a very small step. That's kind of the goal, right? You start with high Fertile, go through many passes, you keep lowering, keep removing these complicated things and turning them into simpler things. Take those when statements, turn them into muxes, take those undefined bit widths, figure out what those bit widths should be. And eventually you get down to low Fertile and everything is all specified. All the operations are things you recognize. And going from low Fertile to Verilog is much, much simpler. And so that's transforming kind of from one language to another, going from chisel to Verilog. But these passes and these transformations can do a lot of things, right? They can analyze your design. You can get certain analytics or details. Years ago, Intel had a project where they use Fertile to kind of get early hardware cost estimates for a design. Unfortunately, that's been bit rotten and not currently compatible in this version of Chisel 3, but that was a kind of cool project they did. You can optimize design. That was the original motivation for today's lecture, right? Let's say you want to build a optimization that's kind of encapsulated. Well, guess what? If you can perform an optimization to Fertile, you can do that. Other things you can do are instrument or specialize the Fertile. So, for example, if you've worked on a real industrial project, you've may have had to deal with things like called scan chains, right? Where you have your design works the way you hope it does. However, when it comes to debugging or testing that design, you want to do what's called a scan chain. Basically, kind of insert wires to dig into all the internal registers of your design to set them and probe them, etc. Now, having that in your chisel, you can do that. You can have, um, additional fields in all your modules. You could also imagine um, maybe have some nice cleanness with Scala and Chisel. Maybe having like a trait, and you add that trait and does the scan chain insertion for you. But that requires modifying those modules. That requires modifying those generators. What if instead you knew you had a very specific kind of scan chain you want to build for your project? You can write that as a tool, as a fertile transformation, and now you don't need to modify the original design. So choices, right? Fertile makes a lot of things possible. Um, so I've kind of already mentioned some of these, but maybe make this more concrete. What are some example lowering passes, right? Like I said, um, inferring whiffs for bit whiffs. Um, Sometimes you have operations where both operators are different whiffs, and there's rules in Chisel and Fertile for how it has to interact, and that's maybe perhaps add those whiffs to make things match up. As I said, expanding wens, turn these wens into muxes and other connections. And a lot of safety checks are done by Fertile, right? So Chisel front end can be kind of simple, and some of these other safety checks are done by Fertile. It's done in cooperation. There's some safety checks done by the Chisel front end, some done by Fertile. All combined, hopefully we can do a lot of checking at tool time rather than debugging assimilation. As I said, it's not just lowering, it's optimizations. Something's like a lot like compiler optimizations, right? So something like constant propagation, okay, if I have a literal, it's assigned to a reference, I use a reference someplace else. If I plug that literal in to the place where it's used, maybe I can simplify the logic around that. Or what if I'm doing something called dead code elimination, DCE, i.e. pruning? Look at the inputs, look at the outputs. If there's hardware that's not attached to either, you can probably snip that away, right? Or common social expression eliminations, CSE. Deduplicate things that are repeated is a common trick. So these are all things you can kind of do. It says a lot of sounds very compiler-like, and that's intentional, right? These are best practices from decades of experience we're leveraging in the hardware community to kind of do stuff better. So as a shining beacon of what's possible, something like Fertile, I'm going to pitch what's called the FireSim project, right? So what it does is actually pretty impressive. Um, so let's say you have a large hardware design and you want to simulate it. You may find that the simulators are crazy slow, right? So in this course, we don't have very big designs, so much of it's not too wrong. But remember, like a real ASIC is going to be in the gigahertz, right? How fast it runs. You have a big enough design with a software simulator, your simulation speed is going to be under a kilohertz. So you're talking, do the math, right? 10 to the 9 versus 10 to the 2, 10 to 7, maybe a 10 million times slowdown. You're not going to be able to run very many cycles before you run out of time. So FireSim is technology to take a chisel design and run an FPGA. Now, of course, you can always take hard designs, put on FPGAs, but what is the key challenges here? There's a few. Number one, what happens if your hard design is too big for the FPGA, right? How do you split it across multiple FPGAs? That's a challenge. Number two, what do you do if your FPGA is running at 100 megahertz, which is pretty good for FPGA, and the memory it's talking to is running at real memory speeds? Now all of a sudden the memory in the simulation are running at incompatible speeds compared to the real world. You can virtualize time. So what you want to do, of course, is dive in to design and add all sorts of time tracking and virtual tokens to make sure you are doing the right thing to track the time. And so what's cool about this is that FireSim appears to be this kind of magic tool from the outside, and of course can run this on cloud FPGAs, but under the hood, it's going through the Fertile, instrumenting it, modifying it, etc. This is all great. So FireSim was the original paper from years ago. There's been a variety of follow-on papers. For example, Golden Gate looked for opportunities to improve resource efficiency by sharing and multiplexing objects. I need to revise the slides tonight to add on FireAxe, which is technology to help with the partitioning process when you have a design big enough to go across multiple J's. How do you pick which goes where? The reason I'm bringing this up was this is a really impressive project set of projects built by grad students that was otherwise require dozens of teams of commercial engineers years, right? This is all possible because of the Fertile library, right? So the Fertile library lets them do this. All the stuff involving, parsing the input design and then the output, they don't need to worry about. All they need to do is make Fertile transformations. They can leverage all the work that's already been done in the chisel front end, all the other useful things they have to process Fertile. For example, maybe you change the Fertile and then you want to call optimizations to then modify that Fertile. Sure, you can do that. That's the advantage of having a library. So they're able to reuse so much. So if you give me a second, I'm going to break the slide up. I don't know why they are being shown as one slide. Um, now I'm going to shamelessly pitch my own research in my own research group, but here's why. So for example, research that I've done in my own group is something called Essent, which is an RTL simulator, right? So we take in hardware designs and we make a really fast simulator, usually the fastest, both for single thread and multi-threaded. And how is that possible? Well, we didn't have to do an entire tool chain. We just had to take in Fertile and then fill us with Flex code. Um, and so how is that done? Well, we use this Fertile library. We're able to kind of see the hardware design. We can go around and crawl it, do what we need to do. So when the dust kind of settled on this project, the SN code, which is in Scala, is only about 5,000 lines, right? Basically, we have a lot of secret sauce on how we do things fast for simulation. And that's where we spent all the effort doing that. And then we compare it to something like Verilator, which is, very commonly used open source Verilog simulator. It's over 100,000 lines with Flex code, right? And not only is it, many times smaller code base, it's at least 2x faster, if not more. One of the students in the group has made something called RepCut, which does multi-core parallelization. If you count multi-core parallelization, RepCut can really outperform Verilog by quite a big margin, much more than 2x. The kind of question is, wait a second, what the heck's going on here, right? So what's going on here is that because of the productivity advantages of both Scala and this Fertile library, there's so much stuff for processing and building a hardware tool that we didn't have to do that was already in the Fertile library. So as a result, we as researchers spent all of our time thinking about new simulation techniques and optimizations to go fast. And that's why we're faster is we spent more time on optimizations. Verilator does only a handful of optimizations because it's just so much code to parse Verilog and then emit things correctly. So now, of course, in the spirit of fairness, yes, um, there are a couple of Verilog constructs that Verilog can simulate that Essent cannot, because Essent only simulates Fertile, and some of those Verilog constructions aren't available in Fertile. However, I include this anecdote, like I said, to be aware of the fact, yes, you can go out and build impressive hardware tools by leveraging one of these hardware IRs. Cool. So then Circuit, which is the next frontier, I should say, it's the current frontier. So this is what's kind of subsuming everything right now. So it's a hardware IR, leveraging LLVM. So earlier I pitched how impactful LLVM was for compilers. If you're writing C code, maybe you're perhaps using Clang. That's LLVM based. Perhaps you like Rust. That's LLVM based, right? And so it's really kind of a lot of languages, a lot of great things over there. And so that both organization and code base and some of the pieces from there are being used for hardware IRs, right? And so Circuit's the project that's doing that. So the way it's being structured is Circuit's actually a very general, very flexible, very inclusive IR. It has a lot of different things. They have a something called dialects. And so there's multiple dialects. One of those dialects is Fertile. There are other semantics if you want to describe certain things and other ways of describing hardware that are also supported. So that's the IR. There's also a tool that implements this, which is, for example, FurTools I was talking about. This was, largely developed by Sci-Fi because, yes, it's compared to the original Scala Fertile library, it's a lot faster, a lot less memory. And so that's the direction things have gone. And so, although Fertile still uses the front end to kind of feed into this circuit, um, that's kind of standard. And so this Fertile Scala library we're using, it's been end of life. So as the future, as they change Fertile, which they haven't done too often, if they were to change Fertile, that will be reflected both in the chisel front end and in this tool called Circuit, Circuit tool using FurTool. it may not necessarily be reflected inside that Scala-based Fertile library, right? Shucks. But that gap for now isn't too bad, but maybe in a couple of years, there'll be a bigger gap. But Circuit's really cool. There's a lot of people using it for a lot of different projects, academic, industrial, etc. Um, so guess what? If you want to build a custom standalone tool, you can do some pretty cool stuff with it. It has a higher barrier of entry than the Scala-based tool. So remember before with Scala Fertile, I mean, you write your design in Scala as Chisel, right? You can add some other classes and do something to Scala Fertile. You saw in that thing here I was showing you. I mean, you can get to the Fertile intermix of your code, right? I showed you that, um, right? It's this intermix. You can get there. Uh, with Circuit, now all of a sudden you got to start writing C++ code and writing a separate code base. It's a little bit harder to get started, but you still can write your own custom tools and stuff like that. Cool. So hopefully today, I talked mostly about Fertile. What I described applies to most hardware IRs. And that's kind of the point, is rather thinking just about making a design, which you maybe came into this course thinking about, throughout this quarter of time, I encourage you to think about making a generator. And now thinking about, not just generators, about actually making full-on tool like transforms or even tools themselves. And so there are multiple hardware IRs out there. So Fertile is one of the more popular recent ones. So it kind of, was being carried along by Chisel. If you've heard of Yosis, a very commonly used open source tool, they have their own RTL IL. I just talked about Circuit, which is kind of this big future going out there. Um, Fertile originally came out of Berkeley, so a lot of other top universities had their own competing IRs. So, for example, at Stanford, they had Core IR. Um, there was LLHD from ETH, which I still include on the slide. However, the original link no longer works. I checked that last night, and it's now not redirecting correctly. So if there in strike through, the link is now to the paper itself rather than the code. So I guess that's a sign that this code is not being maintained, perhaps. But you still see a lot of IRs out there. And yeah, so between especially RTL, and Circuit, those are kind of getting a lot of current traction. Cool. Any other questions? Cool. That's it, folks.